Every single day, more than 15 billion cigarettes are produced worldwide. That is 173,000 every single second. But how does an ordinary tobacco leaf transform into a cigarette? What happens behind the closed doors of factories, where massive machines work non-stop to roll out thousands of packs every single hour? Today, we will reveal all the secrets, from enormous tobacco plantations to high-tech packaging lines. And you will be shocked at the hidden processes behind this industry. Stick around until the end so you do not miss the most fascinating details. The very first tobacco factory in Europe was established in Seville, Spain, in the year 1728. For over a century, this factory supplied Europe with cigars, generating substantial profits for the Spanish treasury. Today, Europe is home to major tobacco companies such as British American Tobacco, Philip Morris International, and Imperial Brands. For instance, in the year 2024, Imperial Brands reported an operating profit of £3.5 billion British pounds, which was 4.5% higher than the previous year. This growth was driven by a 26% increase in revenue from alternative products, such as electronic cigarettes and nicotine pouches. Growing tobacco requires a specific climate, as this plant thrives in warm weather and fertile soil. The primary regions for tobacco cultivation include North and South America, Africa, Southeast Asia, and Europe. The leading countries in tobacco production are Brazil, China, India, the United States of America, Zimbabwe, Turkey, and Italy. China is the world's top tobacco producer, cultivating more than 2 million metric tons of tobacco leaves annually, which accounts for over 40% of global production. The key tobacco growing regions in China are Yunnan, Guizhou, Hunan, and Sichuan provinces. India produces approximately 800,000 metric tons of tobacco per year, primarily in the states of Andhra Pradesh, Telangana, and Karnataka. Tobacco seeds are sown in the spring, and the leaves are harvested several months later. This process can take several weeks since each layer of leaves is collected separately. After harvesting, the leaves are transported to specialized facilities, where they undergo fermentation and drying. The most common drying methods include air curing, fire curing, or sun curing, depending on the type of tobacco. For instance, Virginia tobacco is fire cured, meaning the leaves are hung in curing barns where the temperature is carefully maintained using heated air. This process lasts about 7 to 10 days and gives the leaves a golden color and a mildly sweet aroma. Burley tobacco, on the other hand, is air-cured in shaded barns for an entire month, resulting in a more intense and dry flavor. After drying, the tobacco leaves go through fermentation, which helps reduce nicotine levels and remove excessive bitterness. This fermentation process can last several months. A large portion of the tobacco used for cigarette production in Europe is imported from Brazil, Zimbabwe, China, and the United States of America. Some countries, such as Italy, Greece, and Turkey, cultivate their own tobacco, which is also processed in local factories. Every batch of tobacco arriving at production facilities undergoes strict quality control, where factors like moisture content, color, and nicotine levels are analyzed. The process begins with the initial treatment of tobacco leaves. First, the leaves are sorted by quality and type, with damaged or unsuitable parts removed. On average, each cigarette contains approximately 1 gram of tobacco, meaning that large factories process hundreds of metric tons of raw materials daily. After sorting, the tobacco is processed in manufacturing plants, where machines take over most of the work. The leaves are first shredded into fine fibers. Machines meticulously control the size of these shredded pieces to ensure uniformity. Then, the tobacco undergoes steam treatment to increase its elasticity and improve storage conditions. Various flavorings and stabilizing agents are added to regulate moisture levels and enhance taste characteristics. Typically, cigarette blends include a mix of different tobacco varieties to achieve the desired flavor and strength. The next stage is cigarette formation. Production lines are equipped with specialized machines capable of rolling out more than 20,000 cigarettes per minute. These automated lines operate with incredible speed and precision. The process begins with shredded tobacco being evenly distributed onto a conveyor belt. Next to this belt, a continuous strip of cigarette paper is unrolled. The machine wraps the tobacco in the paper, forming an uninterrupted tube that resembles a long roll. This roll moves along the belt at high speed, and special cutting blades then slice it into individual cigarettes, each approximately 3 inches long. Filter production is a separate process that begins with a primary material, usually acetate fiber. This synthetic polymer is derived from cellulose, which comes from wood pulp. The fibers are treated with special chemicals to give them the required structure, after which they are pressed and formed into long strips. To bind the fibers, a plasticizer called triacetin is used, ensuring the filter maintains its shape. These long strips are rolled into cylindrical blanks, which can be several feet long. They are then cut into smaller sections that match the required filter length. On the production line, these filters are fed into a specialized mechanism that wraps them in a thin paper layer to reinforce their structure. A standard filter can weigh between 10 and 20 grams, depending on the type, and its volume can range from 1 to 3 milliliters. In large-scale manufacturing, several metric tons of acetate fiber may be processed daily, with the total volume of filters produced reaching hundreds of thousands of liters. Next, the filters are attached to the tobacco rod. This is done using wrapping paper that is bonded with food-grade adhesive to create a strong connection between the filter and the tobacco-filled portion. In the bonding area, the wrapping paper passes through a roller that evenly applies the adhesive to its surface. The filter and the tobacco rod are then precisely aligned and merged using a specialized mechanism. The wrapping paper is tightly wound around the connection point and firmly pressed to ensure a secure bond. This process happens in a fraction of a second, and each minute, the machine can attach hundreds of filters to tobacco rods. Throughout production, the total amount of adhesive used can reach several dozen kilograms per shift, while the length of tobacco rods passing through the equipment is measured in hundreds of yards. Once assembled, the cigarettes move along the conveyor to the inspection section, where the strength of the bonds, uniformity of the wrapping, and adherence to standard dimensions are checked. Special scanners and weight sensors examine each cigarette to detect any defects, such as hollow spots, uneven tobacco distribution, or damaged paper. Any defective items are automatically removed from the line. Another crucial step is the application of tracking codes on each cigarette or filter, ensuring full traceability throughout the production cycle. This is done with high-precision laser markers that do not damage the paper. Finished products are then cut to final lengths if needed before reaching the packaging section, where they are grouped into packs of 20 and wrapped in foil. Once cigarettes are paired with filters and pass quality control, they move to the packaging stage. First, the cigarettes are aligned on the conveyor, forming groups based on the intended pack size. A standard pack typically contains 20 cigarettes, although there are variations with 10 or 25 pieces. Once grouped, the cigarettes are wrapped in an inner lining made of foil paper or thin aluminum foil to maintain freshness and prevent drying. They are then automatically placed into cardboard boxes, which arrive via a separate conveyor. These boxes are made from thick cardboard that is pre-cut, folded, and glued using high-speed machinery. The packs then pass through a wrapping mechanism, which seals them in a thin, transparent film. This film includes a perforated strip for easy opening. At this stage, excise stamps and barcodes are printed. On average, a single packaging line can process about 15,000 packs per hour. Completed packs are arranged into blocks of multiple packs, usually 10 per block. These blocks are further wrapped in film or packed into cardboard boxes before being placed onto pallets for transportation. Large cartons can hold up to 500 packs each. The boxed products are stored in factory warehouses until they are shipped to distributor warehouses. From there, cigarettes are sent to stores, supermarkets, and specialized kiosks. Every day, dozens of trucks leave major tobacco factories, delivering millions of cigarettes to distributors and retail locations. The entire journey, from manufacturing to store shelves, can take anywhere from a few days to several weeks, depending on logistics and market demand. At large tobacco factories, machines operate continuously across multiple shifts. In a single workday, one of these machines can produce several million cigarettes. Modern cigarette manufacturing is characterized by a high level of automation, minimal human involvement in production, and rigorous quality control at every stage. Factories are equipped with air quality management systems to maintain stable humidity and temperature, which are crucial for preserving tobacco properties. A typical tobacco factory can produce up to 200 million cigarettes per day, amounting to thousands of metric tons of finished products each month. Every single day, airplanes across the world consume more than 5 million barrels of aviation fuel. This fuel is the lifeblood of aviation. Without it, not a single jetliner would take off. But have you ever wondered how it is made? From oil refineries to the ultra-pure tanks inside aircraft, the journey of jet fuel is packed with chemical secrets, strict regulations, and even technologies originally developed for military fighter jets. Today, we are pulling back the curtain on this fascinating process and uncovering all its secrets. Jet fuel is a crucial component of the aviation industry. It must meet stringent quality standards to ensure the stable operation of both turbojet and turboprop engines. The primary source for jet fuel production is crude oil, which undergoes a complex technological journey from extraction to the final product. It was obtained through the distillation of crude oil. In the year 1903, the Wright brothers made the first controlled flight with the Wright Flyer, powered by a gasoline engine. In the early days of aviation, gasoline remained the primary fuel, as piston aircraft engines required a high degree of fuel volatility. However, during the 1920s and 1930s, engineers began considering kerosene as an alternative to gasoline due to its higher energy density, making it more suitable for high-altitude flights. German engineer Hans von Ohain and British designer Frank Whittle independently developed the first operational jet engines. Can you believe it? It is true what they say. Ideas are in the air. So, in the year 1939, Germany tested the first jet aircraft, the Heinkel He 178, which ran on specially refined kerosene. In the year 1941, Britain responded to the Nazis by launching the Gloucester E into production, the first British jet aircraft. Around the same time, engineers began developing special types of kerosene that met the demands of jet engines. Military nations involved in the war experimented with various fuel formulations to ensure high energy density, resistance to low temperatures, and low corrosiveness for fuel systems. During the war, jet fuel had a primitive composition, but over time, its standards improved significantly. After the devastating Second World War, jet aviation began rapidly advancing. This created a demand for improved fuel that could provide reliability at high altitudes, better thermal stability, and the absence of harmful impurities. In the 1950s, the first standardized types of jet fuel emerged. Let's take a look at them. JP1, developed in the year 1944, was an early standard for military aviation. JP4, introduced in the year 1950, was a blend of kerosene and gasoline that improved performance in cold temperatures. JP5, introduced in the year 1952, had a higher flash point and was used on US aircraft carriers. Commercial aviation also introduced its own standards, and in the 1950s, Jet A and Jet A1 were introduced as the primary fuels for commercial aircraft. With the development of supersonic aviation, such as the Concorde, and new generation military aircraft, the demand for higher quality fuel increased. Fuel now needed a lower freezing point, as flights took place at extremely high altitudes. This led to the introduction of anti-static and anti-corrosion additives, improving safety. Fuel systems were also designed to prevent icing, as jet fuel could cool down to -40 degrees Fahrenheit or lower. In the 1980s, the military adopted JP8, replacing JP4. This new standard contained fewer volatile components, making it safer to store and transport. The 1990s marked the beginning of the modern era of jet fuel production. So, let's move on to the steps involved in making jet fuel today, starting with crude oil extraction. Jet fuel is derived from hydrocarbons found in crude oil or natural gas. There are several methods for extracting crude oil. The first method is natural pressure extraction, where oil flows to the surface due to its own pressure. This is common in young oil fields. The second method is mechanical pumping, where pumps are used to lift the liquid to the surface. The third method is secondary recovery, where water or gas is injected into the reservoir to increase pressure and stimulate oil flow. Once extracted, crude oil contains impurities such as water, gases, and solid particles that must be removed before refining. Before transportation to the refinery, crude oil undergoes purification. First, water is separated using separators and chemical agents to remove emulsions. Next, degassing removes light gaseous hydrocarbons. Finally, filtration removes solid particles. In storage tanks, the flow slows down, allowing heavier particles to settle, while lighter fractions rise to the top. After this preparation, crude oil is transported to refineries through pipelines or by tanker ships. The next step is the separation of crude oil into different fractions. Let me explain how this process works. The process begins by heating crude oil to temperatures between 662 and 752 degrees Fahrenheit inside a massive distillation column. Through evaporation and condensation, we obtain different fractions: gaseous hydrocarbons, gasoline, kerosene, diesel fuel, and residual fuel oil. The gaseous hydrocarbons include methane, ethane, propane, and butane. The kerosene fraction serves as the primary raw material for jet fuel and undergoes further purification. To improve the quality of the kerosene fraction, it is treated to remove sulfur, nitrogen, and oxygen-containing compounds through hydroprocessing. This process occurs under pressures ranging from 30 to 80 atmospheres and at temperatures between 572 and 752 degrees Fahrenheit, using catalysts such as nickel molybdenum or cobalt molybdenum compounds. As a result, sulfur content is reduced, minimizing corrosion and harmful emissions. Additionally, fuel stability improves, allowing for longer storage without sediment formation. If crude oil does not contain enough kerosene fraction, catalytic cracking or hydrocracking is used to break heavier fractions into lighter ones. Catalytic cracking employs catalysts to break large molecules into smaller ones, while hydrocracking uses hydrogen to produce stable hydrocarbons. These processes help increase the yield of kerosene for jet fuel. After purification and modification, special additives are added to the kerosene fraction to enhance its properties. Antioxidants prevent sediment formation and maintain fuel system cleanliness. Anti-static additives reduce the risk of electrostatic charge buildup during refueling. Anti-corrosion agents protect fuel tanks from corrosion. Anti-freezing additives ensure stability at low temperatures. After additives are introduced, the fuel undergoes final filtration and preparation for distribution. To meet international standards, jet fuel undergoes strict quality testing. Viscosity determines fluidity at low temperatures. The freezing point for Jet A1 must not exceed -52.6 degrees Fahrenheit. The heat of combustion must be at least 18,400 British thermal units per pound. Water content must not exceed 0.462 thousandths of a grain. Electrical conductivity ensures safe refueling without sparks. If the fuel fails to meet standards, it is sent for reprocessing. And now, we reach the final stage of our journey. The finished jet fuel is stored in tanks with moisture and temperature protection. It is transported primarily through pipelines to airports. Large volumes are shipped by rail tankers. Tanker ships handle international deliveries. Trucks deliver fuel to remote airports. During transportation, it is crucial to prevent contamination with water or foreign substances that could compromise fuel quality. By the year 2025, the United States is projected to consume nearly 2 million barrels of aviation fuel per day, totaling approximately 86 million tons per year. As one of the world's largest consumers of jet fuel, the global demand is expected to be significantly higher. The aviation industry is actively working on developing renewable jet fuels to reduce greenhouse gas emissions and improve sustainability. With advancements in technology and environmental regulations, the future will see wider use of biofuels and synthetic alternatives, making aviation more eco-friendly. And most importantly, jet fuel keeps airplanes flying. The next time you board a plane for a vacation or business trip, remember the complex production process that brought that fuel to the aircraft. I think it is worth it. What do you think? What if I told you that every bottle you throw away could live an infinite number of lives? Ardagh Group creates more than 160 million packaging units each year, using thousands of tons of recycled glass. Now imagine the scale: industrial crushers that process up to 3 tons of glass per hour, and furnaces working at full capacity to give this material a new life. What does this grand transformation look like? Keep watching. You will be amazed. The company participates in various programs aimed at reducing landfill waste, actively collaborating with municipalities and other organizations to collect and recycle glass. Through these efforts, Ardagh increases the proportion of cullet used in production, as reusing glass is more energy efficient than making new glass from raw materials. For example, the company supports deposit packaging systems, where consumers return used glass bottles for recycling. They also work with waste sorting centers, providing equipment to clean and prepare cullet for processing. In many countries, Ardagh funds community education programs to raise awareness about the importance of recycling glass. Through these initiatives, Ardagh Group not only minimizes landfill waste, but also significantly reduces production energy costs, as glass made from cullet melts at lower temperatures. This is an essential part of their sustainability strategy, focused on conserving natural resources and reducing environmental impact. Each year, the company produces over 160 million packaging units, highlighting its scale and importance in the global market. Thanks to advanced technologies and high manufacturing standards, Ardagh Group remains an industry leader, contributing to economic development and environmental responsibility. The story of Ardagh Group began in 1932 in Dublin, Ireland, when the company started as a small glass packaging manufacturer. Its founders aimed to meet the growing demand for glass bottles, driven by the expanding food and beverage industries. In its early years, the company produced bottles for local breweries and dairy businesses, gradually increasing its scale. A pivotal moment came with the strategic decision to expand through acquisitions. In the 1990s, the company began acquiring plants specializing in glass containers across Europe and beyond. It later entered the metal packaging sector, diversifying its business and tapping into new markets. Today, Ardagh Group is a global leader in packaging production. Its growth story is one of transforming from a small regional manufacturer into a world-renowned corporation that remains committed to its mission, creating high-quality, sustainable packaging that meets the needs of the modern world. Ardagh Group embraced the use of recycled glass as part of its commitment to addressing contemporary environmental challenges and economic trends. Glass is an ideal material for reuse, as it can be recycled an infinite number of times without losing quality. Over time, the company realized that transitioning to more sustainable production practices was not only an ethical necessity, but also a powerful business strategy. Several factors influenced this decision. First, growing demand from customers seeking eco-friendly packaging. In a world where more people are concerned about climate change and pollution, glass containers made from recycled materials have become an attractive solution for many brands. Second, economic benefits. Using recycled glass reduces energy costs. Melting cullet requires 30% less energy than producing new glass. This, in turn, lowers carbon emissions. Thus, using recycled glass has become a key part of their business, supported by both environmental and economic advantages. Garbage trucks deliver collected glass to specialized recycling facilities. There, it is first inspected to sort out materials unsuitable for recycling, such as ceramics, plastic, or metal. Next, the glass is crushed into cullet, small pieces that are easier to melt and clean. This cullet is then transported to glass manufacturing plants, where it is used as raw material for producing new bottles, jars, or other glass containers. The glass arriving at the recycling plant is initially inspected and sorted. Automated systems or manual processes remove foreign materials, plastic, metal, paper, or ceramics, that could disrupt further processing. The company employs approximately 20,000 workers globally. Before crushing, the glass is washed. Powerful systems rinse away dirt, labels, and product residues. High-pressure water jets remove everything: dried ketchup, wine remnants, stuck-on labels, and even tiny bits of paper that seem impossible to clean off. This step is crucial for ensuring the purity of the raw material. Water streams splash everywhere as the glass passes through special brushes and rollers spinning at high speed, polishing each piece to a shine. The noise resembles a small waterfall storm. Watching clean, perfectly shiny glass emerge from the machines is a spectacle, transforming what was once dirty and labeled into something pristine. It feels like magic, but it is actually cutting-edge technology at its best. The cleaned glass moves into specialized crushers. There, it is ground into small particles using powerful mechanical hammers or rollers, resulting in fragments ranging from a few millimeters to several centimeters. This material, known as cullet, resembles gravel. Industrial hammer crushers can process up to 3 tons of material per hour. To remove any remaining foreign materials, the cullet passes through magnetic separators for metals and air jets for plastic and paper. Additionally, laser or optical scanners automatically sort the glass by color into clear, green, and amber categories. Sorting glass by color is not merely an aesthetic choice, but a critical technological process with several practical benefits. Colors affect the final quality and properties of the new product. For instance, clear glass is used for beverage or cosmetic bottles and must be kept as pure as possible. Green or amber glass, on the other hand, is ideal for packaging that protects contents from ultraviolet light, such as beer or wine. Color sorting is also essential for melting, as each glass type has unique temperature and chemical characteristics. Mixing colors can destabilize the process and risk producing defective batches. Mixed colors are harder to recycle. Such glass is often sent to lower priority uses or not reused at all, increasing waste. Properly sorted glass reduces energy consumption during recycling, as there is no need to clean the material of color impurities. Therefore, color sorting not only ensures the purity and quality of new glass, but also significantly reduces energy costs and maximizes the use of recycled resources. The finished cullet is stored in bins or bags and transported to glass manufacturing plants. Depending on the requirements, it is used as raw material for producing new glass. Though cullet appears sharp, storing it in bags is entirely feasible due to specialized materials. These bags, called big bags or flexible intermediate bulk container, are made of ultra-durable polypropylene with multiple layers that prevent tearing, even from sharp glass edges. Sometimes, the inner layer of big bags is additionally coated with laminated material for extra strength and dust resistance. The cullet, reduced to pieces ranging from a few millimeters to several centimeters, has edges that are less likely to puncture the bag material. Storing in such big bags is not only safe, but also highly convenient. The bags are easy to transport, stack, and dose for further use in furnaces. After preparation, the cullet is transported to Ardagh Group factories, where it is transformed into new glass products. A significant portion of the cullet is loaded onto trucks, either standard or specialized, depending on the volume and route. For larger shipments, even rail cars are used to cut transport costs and reduce the carbon footprint. Upon arrival at the factory, the cullet undergoes another inspection. This ensures that the material meets all requirements, such as the absence of any foreign impurities or pieces of the wrong color. Afterward, it is fed into melting furnaces, advancing the recycling process to the next level. Incidentally, the closer recycling plants are to manufacturing facilities, the more economically and environmentally efficient the entire chain operates. This is another reason why Ardagh Group actively supports local glass collection and recycling systems. Have you ever wondered how the beer you drink is made? Imagine this: 1 million tons of grain every year, thousands of bottles filled every minute, and automated machines working with millimeter precision. We are diving into the world of brewing at the Anheuser-Busch factory, the largest beer producer in the world. We will discover how ordinary barley transforms into a hoppy beverage, and why every drop of Budweiser undergoes meticulous quality control. This is not just production. It is a spectacle of scale, flavor, and innovation that you absolutely will not want to miss. Did you know that the average American drinks about 2,500 ounces of beer annually? And while the Czech Republic and Germany lead in beer consumption, Anheuser-Busch supplies a significant portion of the global demand. It all begins with humble barley. At the factory, I witnessed how tons of grain are delivered and processed before being turned into malt, one of beer's main ingredients. Everything here is automated. Specialized machines grind the grain and soak it in water to wake up the enzymes. It literally looks like a dance of machinery, with each piece knowing its role precisely. In enormous steel tanks as tall as a 3-story building, giant machines load tons of golden barley. You can hear the soft, calming sound of the grain cascading downward, reminiscent of gentle rain. What happens next is pure technological magic. Special machines delicately grind the grain, exposing its core, starch. It looks as though the grain passes through a massive waterfall, transforming into a light, fluffy powder. This powder then ends up in enormous vats filled with warm water. Here is an interesting fact. The machines do not simply soak the grain in water. They maintain an ideal temperature and humidity level, like a steam bath designed to activate the enzymes. You can see the vats come alive with hot steam passing through them. Water mixes with the ground grain, forming a thick, creamy mixture that begins to release the aroma of freshly baked bread. This moment feels incredibly vivid. It is as if the grain awakens and starts working together with this mechanical orchestra. The malt vat begins to rotate. Yes, it does not just sit still. It practically dances, with special paddles mixing the blend so the enzymes activate evenly. Steam rises, forming a light mist that fills the room with a sweet aroma. Sometimes this steam is lit with special lamps, adding a touch of spectacle, as if you are witnessing a scene from a sci-fi movie. And this is only the beginning. The porridge then passes through other tanks equipped with precise filters that separate the liquid, the malt extract, from the leftover grain. Now imagine this happening on a scale where a single processing cycle can fill thousands of bottles of beer. This is not just production, it is a full-scale performance. The machines operate with the precision of fine jewelry, and as you stand nearby, you feel like a witness to something monumental. The entire process is filled with rhythm, aromas, and sights that will make you forever respect beer. Though, to be honest, I already respect beer because it sponsors my enjoyable Friday nights. Anheuser-Busch sources barley from various farms, and the quality is scrutinized down to the smallest detail. Different beers require different malts. Lager? A light malt base is needed. Stout? Add darker, roasted malt. You get the idea. They use around 1 million tons of grain annually for beer production. Now for the most exciting part. These giant steel fermentation tanks are so enormous that it feels like you could fit an entire football team inside one. This is where the magic begins. Maltwort, a sweet liquid extracted from the grain, is mixed with hops and yeast. Honestly, the smell in the fermentation hall is something else. It is a warm, rich aroma, reminiscent of bread and fruits. The yeast here works like crazy, turning sugar into alcohol and carbon dioxide. Fermentation lasts anywhere from several days to a few weeks, depending on the type of beer. The factory employs about 4,000 people. It is like a small town. But what surprised me the most is the level of automation. People here mostly monitor the process from screens while the machines handle the bulk of the work. Even the smallest details, like the temperature and pressure inside the tanks, are controlled by computers. Honestly, the factory feels more like a scientific laboratory than a traditional brewery. And it did not start out this technologically advanced. Anheuser-Busch has an incredibly fascinating history. It all began in the year 1852, when a small brewery opened in St. Louis, simply called Bavarian Brewery. In the 1860s, it was purchased by Eberhard Anheuser, a German immigrant, and his son-in-law, Adolphus Busch, joined the business a few years later. That is when the real boom began. Adolphus Busch was not just an entrepreneur, but an innovator. Imagine this. In the year 1876, They created Budweiser, the first American lager beer. To make it accessible anywhere in the United States, Busch introduced revolutionary transportation methods, such as refrigerated railcars. This was a game changer for the beer industry. Today, Anheuser-Busch is part of the AB InBev Corporation, the largest beer producer in the world. Their brands, Budweiser, Michelob, Stella Artois, Corona, are recognized on every continent. According to AB InBev, Budweiser alone is sold in over 85 countries, producing over 2,064,000,000 gallons of beer annually. On average, each production line fills 1,500 bottles or cans per minute. The bottling line is a true showcase of technical perfection. Hundreds of cans and bottles flow in rapid streams, perfectly aligned, gleaming under bright lights. The entire process is fully automated, and watching it is like observing a finely tuned clock mechanism, but on an enormous scale. First, empty bottles or cans enter the conveyor. They are thoroughly washed to remove even the tiniest specks of dust, because cleanliness here is paramount. Machines spin each container under spiral nozzles that shower them with jets of water. Next comes the filling stage. Cans line up under high-precision dispensers that pour the exact amount of beer into each one in mere fractions of a second. Interestingly, this happens in near-vacuum conditions. Why? To prevent foam formation and avoid any contact between the beer and oxygen, as this could affect its flavor. The next step is sealing. Caps for bottles or lids for cans are fed onto the conveyor through a separate line, and special automatic clamps secure them with such speed that it is almost impossible to see the movement with the naked eye. Then comes the packaging. This is where the real conveyor magic happens. Bottles, cans, kegs, everything moves at lightning speed. More than 1,500 bottles are filled and sealed every minute. Watch this rhythm. Every can undergoes a seal test before moving on to packaging. Here is another interesting detail. Bottle coloring and label printing are also automated. Conveyors move, machines blink, and staff only occasionally intervene to ensure everything runs smoothly. Overall, lasers, sensors, and cameras at every stage ensure quality control. If even a single can or bottle fails to meet standards, the machine instantly removes it from the line. This guarantees that only the best product reaches consumers. Despite the scale of production, the taste of the beer remains consistent. That is their top priority. Every batch undergoes tasting before hitting the shelves. And trust me, this is not just a formality. The tasters here work at the level of true sommeliers. And this is just one factory in the Anheuser-Busch network. In total, the company operates 12 breweries in the United States, along with over 20 distribution centers. Another thing that impressed me, Anheuser-Busch actively works to reduce its environmental impact. For instance, the water used in brewing is purified and reused, and all waste, such as grain husks, is sent to farms as livestock feed. You can now tell your spouse, "Honey, I am not just drinking beer, I am supporting cattle feed in the United States. If you survive saying that, let me know how it goes." Although their largest factories are in the United States, the company has facilities on every continent except Antarctica. By the way, the factory in St. Louis is also a tourist attraction. Every year, they host tours for tens of thousands of visitors. Guests are taken to historic production halls, shown giant tanks, and even get to see their famous Clydesdale horses. And if you are wondering whether you can taste the beer, of course. At the end of each tour, guests are invited to a tasting room to sample the freshest beer. Anheuser-Busch is not just a company, it is a living history of innovation, scale, and tradition. They started as a small brewery in St. Louis and have grown into a giant that is reshaping the beer industry. Next time you open a bottle of Budweiser or Michelob, remember these numbers, this scale, and the people behind every drop of beer. Did you know that over 2 billion cups of coffee are consumed every single day around the world? But how does your morning drink begin its journey from a tiny coffee cherry? Today, we're uncovering the secrets of instant coffee. From the first blossoms of coffee trees to the cutting-edge factories where beans transform into aromatic powder. Why is Arabica so delicate and Robusta so hardy? And how does production involve technologies that seem straight out of a sci-fi lab? Stick around. You'll be amazed by how many hands and minds it takes to create every jar of coffee. Before beans make it to the factory, they travel a long way, from small coffee plantations to industrial mills, and this journey starts long before the beans are ready to work. First, let's talk about Robusta and Arabica. They're like totally different personalities. They grow in different conditions, offer distinct flavors, and have unique growing demands. Fun fact: instant coffee usually uses Robusta, a bean known for its strength and high caffeine content. Arabica is also used, but less frequently, mainly in premium blends to add a smooth, sweeter flavor. Arabica is the premium bean. It's grown high up in the mountains, typically at elevations of 800 to 2,000 feet above sea level. It's picky. It loves mild climates, consistent rainfall, and temperatures between 60 and 75 degrees Fahrenheit. Robusta is less fussy. It thrives in lowlands, can handle heat, humidity, and even pests. Its ideal growing temperature can reach up to 86 degrees Fahrenheit. It's often cultivated in tough climates where Arabica wouldn't survive. Coffee plantations look like small forests. Coffee trees are grown from seeds, and get this, they take up to 3 years to bear their first fruit. Yep, 3 years before those cherries, which aren't even the coffee beans yet, but their outer shells appear. The trees are planted on specially prepared terraces, especially Arabica on slopes. The soil needs to be loose, rich in minerals, and moisture balanced. On many plantations, work is still done by hand, though some larger farms now use machines for planting. Coffee cherries take about 9 months to ripen after the trees bloom. And here's where the magic begins: timing the harvest just right. Handpicking is the best and most precise method. Workers pick only the ripe cherries, leaving the green ones to mature. It's labor-intensive, but guarantees quality, especially for Arabica. Robusta is often harvested with machines that comb cherries off the trees. It's faster and cheaper, but ripe and unripe cherries end up mixed. Handpicking Arabica ensures better quality, but requires a massive workforce. Entire villages or even seasonal workers from nearby regions often help on large plantations. Harvested cherries aren't beans yet, they're just the shells. To extract the coffee beans, cherries undergo processing. There are 2 main methods: wet processing and dry processing. Wet processing is mostly used for Arabica. Cherries are soaked in water, where the pulp dissolves and the beans separate. It's pricier, but results in a clean, delicate flavor. Dry processing is more common for Robusta. Cherries are simply spread out to dry under the sun, and then the shells are removed. It's cheaper, but creates a bolder, more intense taste. After processing, the beans are sorted by size, weight, and quality. The best beans go into premium coffee products, while smaller or slightly damaged ones are used for more budget-friendly options or instant coffee. Here's something cool I learned. Robusta beans are usually round and tougher, while Arabica beans are oval and a bit softer to the touch. Once beans are ready, they're packed in classic jute bags. Why jute? It lets the beans breathe during transportation. On plantations, these bags are often loaded onto small trucks or even motorcycles to reach nearby ports or warehouses. Then, the beans are shipped in large containers that can carry hundreds of tons of coffee at a time. Beans often pass through several countries before reaching the factory. For example, coffee might be grown in Vietnam, one of the world's largest Robusta producers, processed in another country, and roasted or turned into instant coffee at a factory in Europe or the US. Before beans are transformed into instant coffee, they're checked for quality multiple times. On plantations, defective cherries are removed before processing. Before shipping, beans undergo another round of checks at warehouses and ports. This includes examining size, color, and aroma. At the factory, samples from each batch are tasted to ensure the flavor meets standards. Everything starts with coffee beans. At the factory I visited, roasted beans are delivered, and their smell, wow, it's that rich aroma you get when you walk into a coffee shop. Fun fact, roasting follows an incredibly precise schedule. Every second impacts the final flavor. So, where does roasting happen? At roasting facilities. Roasting is a whole universe of its own. It significantly affects coffee's taste and aroma, so it's taken seriously. There are several ways this can go down. Sometimes, especially for large Robusta volumes, beans are roasted in their country of origin, like Vietnam or Brazil. These countries have massive export-focused factories, which cut down on logistics costs. Big brands have their own roasting facilities in key regions. For example, in Europe or the US, there are giant factories specializing exclusively in roasting. Roasting beans separately isn't just a preference, it's logical. Green coffee beans are easier to transport long distances because they're less sensitive to storage conditions. Specialized facilities ensure a consistent roast level needed for specific products. Plus, depending on the end use, instant coffee or ground coffee, beans are roasted differently. Roasting coffee is a science. Beans are heated in rotating drums at temperatures around 400 degrees Fahrenheit. The roast time depends on the desired profile, lighter for softer flavors, darker for bold, intense notes. Instant coffee typically uses dark roasts. This enhances aroma and adds a bitterness that holds up even after processing. Roasted beans are cooled and packed to preserve their aroma. The factory receives this semi-finished product and focuses on its processes. It's a bit like a chef starting with a ready-made base to create a masterpiece. The first step after delivery is grinding the beans to a dust-like consistency. No, this isn't your regular grind for a French press or espresso. Industrial mills turn beans into particles finer than sand grains. Why so fine? I asked one of the staff. The answer was simple. The smaller the particles, the more efficiently the flavor and aroma are extracted in the next steps. Here's where the real chemistry begins. The ground powder goes into special extraction chambers, where it's brewed with hot water under pressure. Think of it as a giant coffee maker. This is where all the flavor and aroma you enjoy in your instant coffee are drawn out. What surprised me? The water temperature is controlled to the exact degree to avoid overbrewing. If it's too hot, the taste becomes bitter. Too cool, and the coffee loses its richness. The extract from these chambers undergoes multi-stage filtration. All unwanted particles are removed, leaving only a liquid concentrate. This concentrate looks like thick syrup and has such a strong aroma, it'll make your head spin. Next comes the most fascinating part. The liquid concentrate is turned into powder or granules using two main methods: spray drying or freeze drying. Spray drying involves blasting hot air to dry droplets of concentrate, leaving behind dry powder. It's fast and relatively cheap, but sometimes loses some aroma. Freeze drying is more complex. The concentrate is first frozen to extremely low temperatures, then sublimated, turning ice into vapor and leaving dry granules behind. It's pricier, but preserves maximum flavor. At the factory I visited, both methods were used depending on the coffee type. For premium lines, only freeze drying was used. The finished powder or granules are packed into jars, sachets, or sticks. It's all automated. Machines measure exact amounts, seal the packages, and add protective valves to preserve aroma. By the way, these valves are a real technological breakthrough. They let air out of the jar, but don't let it back in. You might wonder, how do they keep the aroma? The secret is that some of the coffee oils and aromatic compounds lost during extraction are collected separately and added back to the final product. It's like a little bonus that makes instant coffee so familiar and fragrant. Is instant coffee real coffee? You know, I was a bit skeptical myself until I saw the whole process. It really is 100% coffee, just with a touch of engineering magic. Actually, scratch that, it's more like technical mastery. The difference between instant coffee and freshly brewed coffee is like the difference between homemade pizza and takeout pizza. They're both great, but in different ways. Instant coffee is quicker, more convenient, and still incredibly flavorful when done right. After the tour, I was blown away by how intricate and well thought out the process is. And you know what amazed me the most? The sheer number of people involved, from engineers monitoring the equipment to tasters checking every batch. Yes, tasters. Turns out it's a real profession. Imagine having a job where you drink coffee and evaluate its taste. Isn't that the dream? Instant coffee isn't just powder in a jar. It's a monumental effort, cutting-edge technology, and a love for a drink that brings us comfort, even on the busiest days. So, next time you make yourself a cup, remember the many hands that work to deliver that aroma to you. Imagine every tire on your car as the result of decades of innovation, research, and fine-tuned manufacturing. Goodyear, one of the giants in this industry, produces tires that are engineering marvels. But how exactly are these technological masterpieces made? Let's break it down, step by step, and get a sense of the scale of this incredible work. Goodyear was founded back in 1898 and named after Charles Goodyear, the inventor of vulcanized rubber. The production of Goodyear tires begins with carefully selected raw materials. The key ingredient, of course, is rubber. But not just any rubber you'd find in a forest. This is a complex material made from natural rubber and synthetic substitutes. Natural rubber is harvested from the sap of hevea trees grown in tropical regions. This sap is called latex, a familiar term, right? The main suppliers of natural rubber are countries in Southeast Asia, like Thailand, Indonesia, Vietnam, and Malaysia. To collect the sap, neat cuts are made on the bark of hevea trees, similar to how maple syrup is gathered. Latex slowly oozes out and is collected in small containers attached to the tree trunk. A single tree produces only a small amount of latex daily, so plantations are packed with thousands of trees. Initially, latex has a liquid consistency and needs processing. Acids are added to it, causing the latex to coagulate into an elastic mass. Typically, formic acid is used. Yes, formic acid. Sounds surprising, doesn't it? The name dates back to the 1700s, when scientists first extracted this acid from ants. Back then, chemists boiled ants and discovered a liquid with peculiar properties. It turned out to be an acid that many insects, including ants and bees, use as a natural defense mechanism. Today, no one harvests formic acid from ants anymore. Instead, it's synthesized on an industrial scale from chemicals like methanol or carbon monoxide using modern technology. This method is way more efficient than collecting it from insects. Formic acid works perfectly for latex processing because it's non-toxic in small amounts. It easily coagulates the protein molecules in latex, turning the liquid into a solid elastic mass. Plus, it dissolves in water, making it easy to wash away any residue after treatment. After adding the acid, the resulting material is pressed into blocks or rolls and dried. This process significantly reduces its volume for easier transportation. The dried rubber is shipped to factories worldwide. For Goodyear, this includes plants in the United States, Germany, China, and other countries. The rubber is transported by sea in large bales that are easy to store and use in tire production. This covers natural rubber, but how do they make the synthetic kind for tires? Synthetic rubber is an artificially created material made from petroleum products. Its main component is butadiene, a chemical derived from gases left over after refining oil or natural gas. Butadiene, along with other chemicals like styrene, undergoes a process called polymerization. This chemical reaction links molecules into long chains, creating a material with high elasticity. The most common types of synthetic rubber are styrene butadiene rubber and polybutadiene rubber. To give synthetic rubber the properties needed for tires, such as strength, wear resistance, and temperature resilience, special additives are mixed in, like carbon black or silica, and plasticizers. Synthetic rubber is produced on a large industrial scale and shipped to factories in the form of granules, rolls, or preformed blocks. At Goodyear's factories, a rubber compound is created by combining the best qualities of both natural and synthetic rubbers. The rubbers are weighed precisely according to formulas tailored to specific tire models. In massive industrial mixers, the rubbers are blended with other ingredients: carbon black, silica, sulfur, oils, and chemical additives. Think of it like making dough, but under high pressure and heat. During mixing, the rubber turns into a thick black paste. This stage is crucial because it defines the tire's future characteristics: grip, durability, and temperature resistance. The mixture is repeatedly needed to ensure all components are evenly distributed. This guarantees uniformity in the final rubber. After mixing, the material is cooled and formed into large sheets, which are then cut into pieces for further tire production. The process of cutting rubber sheets at the factory is truly impressive in scale. This isn't done with kitchen knives, but with massive industrial machines that work with the precision of jewelers, but on a factory-wide scale. The thickness of the rubber sheets varies depending on the part of the tire they're meant for. For example, the layers for the tread are thicker than those for the sidewalls. Before cutting, each roll or sheet passes through an automated inspection system. Machines check for defects like air bubbles, tears, or uneven thickness. Anything that doesn't meet standards is immediately discarded. Cutting is done using specialized high-tech machines. Rotary knives, resembling spinning discs, effortlessly slice through the rubber, creating perfectly straight strips. Lasers, the most advanced technology, can cut rubber without physical contact, ensuring extraordinary precision. The laser beam literally melts the material at the desired spot, leaving a flawlessly smooth edge. Depending on the production stage, sheets may be cut into long, narrow strips for tire reinforcement or left in large pieces for the tread. Everything is programmed, and parameters are automatically adjusted based on the type of tire being made. After cutting, materials are sorted by type and size. Strips are rolled up, and sheets are stacked. All of this is transported to the next department for tire assembly. Each machine processes thousands of feet of rubber daily. Powerful engines roar, knives spin at incredible speeds, and workers monitor everything through computers. This conveyor never stops, producing hundreds of tires every hour. It's like surgery on an industrial scale. Everything must be flawlessly precise to ensure the finished tire is safe and high quality. Goodyear is one of the world's leading tire manufacturers, with production facilities in 22 countries and 52 factories. Let's circle back to another fascinating aspect of this story: the ingredients beyond rubber. Why are they added? Carbon black gives the tire strength and protection against UV rays. Silica improves road grip, especially in wet conditions. Sulfur and other chemicals help rubber retain its shape and elasticity under different conditions. As you can see, every detail matters. But that's not all. Let me tell you about the skeleton of the tire. You know it's not just rubber, right? The core consists of a multi-layered structure. The quality of this framework determines the tire's strength, durability, and ability to support the weight of the vehicle. This process involves several sequential and high-tech operations. But first, let's look at the materials. Textile cords are a must in the tire's construction. These are threads made of polyester, nylon, or even aramid, a highly durable synthetic fiber. They provide flexibility and lightness. Steel cords are also added. These are thin yet incredibly strong metal wires that give the framework rigidity and the ability to withstand heavy loads. Rubber acts as the bonding material between the layers of cord, creating a strong yet elastic structure. Cords pass through specialized machines that evenly coat them with rubber. This binds the fibers together, protects the textile or metal from moisture and corrosion, and ensures a strong bond with other rubber layers during vulcanization. This process is incredibly precise. If the rubber layer is too thick or too thin, it could compromise the tire's safety. Next comes the breaker. This part of the framework lies between the tread and the tire's core. Its job is to distribute the load across the tire and protect it from punctures. The breaker is made of multiple layers of steel cord laid at specific angles. Each layer is cut to a template and laid out in a precise sequence on specialized drums. The angles are computer-controlled to achieve the desired characteristics. The main framework is assembled on a special building drum that rotates, allowing all layers to be evenly laid out. First, textile layers are added for flexibility. Then, metal wire rings are added to form rigid sidewalls. These rings help the tire stay firmly on the rim. The tire bead, its inner edge that contacts the wheel, must be extremely strong. The bead ring is made from multi-layered steel strips coated in rubber. Side layers of rubber are added to the main framework to protect the tire from damage. This entire sandwich is secured on the drum using pressure and heat. Every year, Americans consume around 46 million turkeys during Thanksgiving. Ever wondered how many steps a turkey goes through before it lands on your dinner table? And no, it's not just about becoming the star of your holiday feast. From small family farms to massive industrial complexes, the story of turkeys is fascinating, a bit surprising, and definitely worth your attention. Ready to break it all down? Let's dive in. It all starts with eggs. On specialized farms, breeding turkeys lay eggs, which are carefully collected by workers or automated systems. These eggs are then sent to hatcheries. Think of them as nurseries for future birds. In the United States, turkey farms range in size, from small family-run operations to large commercial enterprises. According to the United States Department of Agriculture, 99% of all farms in the country are family-owned. However, medium and large-scale family farms account for 68% of production, highlighting their critical role in American agriculture. The U.S. is one of the world's leading producers of turkey meat. Key turkey-producing states include Minnesota, Indiana, Missouri, and Arkansas. Overall, turkey farms play a vital role in the agricultural sector, supplying a significant portion of domestic consumption and exports. On larger turkey farms, incubation facilities can span impressive areas, designed for the optimal growth of the birds. The size of the farm determines the capacity and automation level of these hatcheries. Eggs are placed in specialized incubators with controlled temperature and humidity. A standard incubator can hold anywhere from 500 to 2,500 eggs. If a farm operates several of these units, the total incubation area can cover hundreds of square feet, depending on the farm's needs. Modern incubators often come equipped with automatic egg turning systems, ensuring eggs stay in the proper position throughout the incubation period. These systems also feature sensors to monitor temperature, humidity, and ventilation, key factors for achieving high-quality hatch rates. After 28 days, tiny turkey poults emerge from their shells. Unlike in nature, where they break the shells on their own, humans often assist the process to minimize losses. Once hatched, the poults are transported to grow-out farms. And by the way, their journey is just getting started. When a poult hatches, it's still reliant on residual nutrients from the yolk absorbed in its abdomen. These newborns need warmth because their bodies can't yet maintain the necessary temperature for normal functioning. Right after hatching, poults are placed in warm rooms, set at about 95 degrees Fahrenheit. Over time, the temperature is gradually lowered to 73 degrees, as the poults develop their ability to regulate body heat. Within a few hours or days, the poults begin seeking food and water. Since incubators provide high temperatures and specific conditions for survival, the young turkeys start consuming water and feed actively within the first hours of life. A crucial step after hatching is creating the right environment. This means constant monitoring of temperature and humidity, along with proper conditions to prevent stress or illness caused by inadequate feeding. Right after hatching, poults are moved to specialized facilities where they get the essentials for survival and growth: warmth, feed, water, and protection from disease. These steps are absolutely critical for their healthy development. Transportation to farms happens as soon as the poults are strong enough for the journey. Typically, they're placed in specialized containers designed for their comfort, constant temperature, ventilation, and enough space to move around. These containers, made from either plastic or soft mesh, ensure the poults can breathe and stay safe during transport. The microclimate inside is carefully maintained to keep the poults healthy. Poults are transported to farms within a few hours of hatching, usually before they start eating or drinking. Feeding begins the moment they arrive at the farm, marking a vital stage in their growth. During the first few days, poults are given a special starter feed packed with essential vitamins, proteins, minerals, and amino acids to support healthy growth. This feed often includes finely ground grains, flour, and feed additives. Water is available 24 hours a day because hydration is critical for young birds. Ensuring they receive vitamins and antibiotics helps prevent diseases and supports proper growth. Over time, the feed is gradually switched to more complex formulations, including turkey-specific compound feed designed to build muscle mass effectively. A turkey's diet consists of grains, protein supplements, vitamins, and minerals. And no hormones. Most countries strictly ban them. Turkeys grow quickly. In 4 to 6 months, they reach an average weight of 15 to 33 pounds, depending on their gender and breed. Massive poultry barns can house thousands of turkeys at a time, equipped with everything they need for comfort: ventilation systems, automatic feeders, and water dispensers. Free range? Forget about it on large farms. Most turkeys spend their entire lives indoors. Why? Because it's easier to monitor their health and prevent diseases that way. When turkeys reach their target weight, they're transported to specialized processing plants. And this is where things get interesting or complicated, depending on your perspective. The birds are loaded into crates, which are then placed onto trucks. Transport usually happens at night or early in the morning to minimize heat stress. While the final destination is the processing plant, ensuring the turkey's well-being at every stage of their journey is crucial. It's not just about the bird's health, but also about economic efficiency, meat quality, and maintaining the producer's reputation. Ethical practices and meeting societal expectations for humane treatment of animals play a significant role here. Let's dive into the details. Even though the plant is the end of the road, the journey there needs to be as humane as possible. This is not just an ethical issue, it's a practical one. Every stage of raising turkeys represents an investment of time, money, and resources. Any significant loss, illness, or injury caused by stress at this point would undermine all the prior effort. Adhering to standards and regulations helps producers avoid scandals or penalties from the government or animal rights groups. Stressed birds often yield lower quality meat, tougher texture, and diminished taste. This directly impacts the producer's reputation. For example, turkeys that experience severe stress before processing can develop a condition called muscle breakdown, which ruins the texture and flavor of the meat. That's why ensuring their comfort until the very end is not only essential for the farmers, but also critical for the final product's quality. Now, we've reached a moment some might prefer to skip. But if you want to understand the entire process, you need to know the truth. Processing at factories isn't for the faint-hearted. Turkeys are stunned using either electrical currents or gas. This is done to minimize stress and pain. The birds are released one by one into designated holding areas or guiding lanes designed for smooth movement toward the stunning zone. These areas are carefully constructed to reduce panic and overcrowding. They often feature smooth surfaces with no sharp edges to prevent injuries. The design ensures that turkeys move in a single direction without pushing or jostling each other. There are two main methods of stunning. In the first, turkeys are guided through a water bath where a mild electrical current is applied. When their heads touch the water, the current stuns them instantly. The second method involves placing them in a sealed chamber where oxygen levels are gradually reduced and gas is introduced. This causes them to lose consciousness without physical pain. In the stunning areas, dim lighting or blue-tinted lights are often used to calm the birds. Factories also reduce noise levels since sudden loud sounds can cause panic. Human contact at this stage is minimized to avoid adding extra stress. After stunning, automated systems handle the slaughter process. The turkeys are then scalded to remove feathers, and later they are either processed into parts or kept whole. Once stunned and slaughtered, the birds are hung upside down on a conveyor belt that moves them through processing zones. The first step is scalding. Turkeys are dipped into large tanks of hot water, typically over 140 degrees Fahrenheit. This process lasts a few minutes and serves two purposes: softening the skin and sanitizing the bird's surface. After scalding, the turkeys are moved into specialized machines called defeatherers, or feather removal machines. These machines are rotating drums fitted with flexible rubber fingers. As the birds pass through, the fingers gently strip the feathers off the body. The rubber material ensures the feathers are removed without damaging the skin. Following this mechanical process, any remaining feathers are checked and manually removed if necessary. This step usually targets small feathers that the machine might miss. The collected feathers aren't wasted. They're repurposed as raw materials for various products, including animal feed, fertilizers, and even certain textiles in some cases. Modern poultry plants use fully automated systems, allowing hundreds, sometimes thousands, of birds to be processed per hour. The high speed of the equipment helps preserve meat quality, as overly lengthy processing can negatively affect texture or appearance. The finished meat is packaged in plastic bags or vacuum-sealed containers and prepared for transportation to stores.